Welcome to Lecture 3 of Business Intelligence and Management Support Systems course. In today's session, we will be exploring the foundational concepts that underpin how data is organized, modeled, and moved within modern business intelligence systems. Specifically, we will examine data models, database schemas, and the pipeline processes that transport data throughout an organization's infrastructure. To frame our discussion, let us begin with an overview of what we aim to accomplish in this lecture. By the end of this session, you should be able to understand how BI professionals employ data models to construct effective database systems, appreciate how schemas serve as organizational blueprints for those systems, and describe how pipeline processes, including ETL, facilitate the movement of data across the system. It is worth noting that BI professionals are not merely answer providers. They empower entire teams by building the infrastructure through which stakeholders can independently access and interpret data. Let us begin with the most fundamental concept, the database. A database is simply a collection of data stored in a computer system. However, for a database to be of any practical use, that data must be meaningfully organized. In the context of BI, we distinguish between two key types of systems: source systems, which are responsible for data ingestion, and destination systems, where data is stored and subsequently acted upon. Understanding this distinction is essential before we proceed to more advanced topics. Source systems are the points of origin for data within a BI architecture. Two of the most common source systems are data lakes and OLTP databases. A data lake stores large volumes of raw data in its original unprocessed format until that data is required for analysis. In contrast, online transaction processing, or OLTP, databases are optimized for data processing rather than analysis. These systems handle operational tasks such as sales transactions and customer orders, maintaining data currency and consistency in real time. Once data has been ingested from its sources, it must be directed toward appropriate destination systems. A data mart is a subject-oriented database that typically represents a subset of a larger data warehouse. It is tailored to serve the analytical needs of a specific business department or function. Online analytical processing, or OLAP, databases, on the other hand, are designed not only for data processing but also for sophisticated analysis. They are capable of drawing upon multiple databases simultaneously, making them particularly well suited to complex analytical queries. Before we can discuss data modeling in depth, it is important to acknowledge the distinction between unstructured and structured data. Unstructured data is data that lacks any readily identifiable organizational form. Audio and video files are common examples. Structured data, by contrast, is data that has been organized in a clearly defined format, typically arranged in rows and columns within tables and relational databases. This structural distinction has significant implications for how data is stored, queried, and analyzed. We now arrive at a central concept for today's lecture: data modeling. A data model is a tool that organizes data elements and defines the relationships between them. Think of it as a conceptual map. It represents how data is theoretically structured within a system and ensures consistency across that system. To construct a data model, BI professionals typically begin with what is known as a design pattern, a concept we will examine in the next slide. A design pattern is a reusable, problem-solving template that employs relevant measures and facts to create a model capable of meeting specific business needs. Design patterns are not unique to any one scenario. They are adaptable frameworks that can be applied across a variety of contexts. You may already be familiar with the most visible output of a design pattern, the database schema. In essence, the design pattern is the template from which a schema is produced. A schema is a description of how data is organized within a database. It serves as the summary of the data model created from a design pattern. Common types of schemas include relational models, star schemas, snowflake schemas, and NoSQL schemas. Each of these schemas describes the structure of data in a particular way, enabling a clear and consistent understanding of how information is organized within a given system. If the design pattern is the template, then the schema is the resulting blueprint. As BI professionals, understanding schemas is fundamental to your work. Many of you will already have encountered relational databases through your prior study of SQL. In a relational database, data is stored in tables that are connected to one another through defined relationships. These relationships are established using primary keys and foreign keys. Consider the example of a car dealership database. The branch YD serves as the primary key in the dealership's table, yet it appears as a foreign key in the product details table, thereby creating a direct connection between these two entities. This chain of relationships can extend further, connecting tables that are not directly linked by way of intermediary tables. Let us formalize these concepts. A primary key is an identifier that uniquely identifies each record in a table. In the context of BI, this may reference either a single column or a group of columns, provided that each row in the table is uniquely identifiable. A foreign key is a field in one table that corresponds to a primary key in another table. Foreign keys are the mechanism by which relationships between tables are established. It is important to remember that only one primary key can exist in a table, though a table may contain multiple foreign keys. Building on our understanding of relational databases, we now turn to dimensional modeling, a specialized relational modeling technique optimized for the rapid retrieval of data from a data warehouse. Dimensional models are structured around three core components: facts, dimensions, and attributes. Each of these components plays a distinct and interconnected role in organizing data for analytical purposes. In a dimensional model, a fact represents a measurement or metric. Facts are the quantifiable, observable data points that capture business activity. A straightforward example would be monthly sales figures. Facts are what we measure. They are the numerical heart of the dimensional model. Dimensions provide context to facts. They answer the fundamental questions of who, what, where, when, why, and how. Returning to our example, if monthly sales is the fact, then dimensions might include information about the customer who made the purchase, the store location where the transaction occurred, and the specific products that were sold. Without dimensions, facts lack meaning. It is the combination of both that enables meaningful analysis. Attributes are the characteristics or qualities that describe a dimension. If a dimension provides context to a fact, then an attribute provides detail about the dimension itself. In a car dealership scenario, the customer dimension might carry attributes such as name, address, and phone number. Attributes are essentially the column labels of a dimension table. They define what information is recorded about each dimensional entity. Dimensional modeling makes use of two types of tables. The fact table is the central table in the model. It contains the measurements or metrics associated with a particular business event. Each row in a fact table represents a single event or the aggregation of multiple events, for example, all sales within a given day. Dimension tables, meanwhile, store the attributes associated with each dimension. These tables are joined to the fact table using foreign keys, providing the contextual richness that makes the data analytically useful. Understanding how these two table types interconnect is fundamental to understanding database design in a BI context. The visual presented on this slide illustrates the structural relationship between fact and dimension tables within a dimensional model. Notice how the fact table occupies the central position, with dimension tables surrounding and connecting to it. This architecture allows analysts to query the fact table while drawing upon dimensional context as needed. an elegant and efficient design for analytical workloads. We can now return to the concept of the schema with a deeper understanding. Dimensional models organize data by connecting facts, dimensions, and attributes into a coherent design pattern. The schema is the final output of this pattern. It is a blueprint that describes the logical definition of data elements, their physical characteristics, and the interrelationships that exist within the model. Crucially, the schema does not hold data itself. Rather, it describes the shape of the data and how it relates to other structures. Every entry in the database is an instance of that schema. The star schema is one of the most widely used schema types in BI. It consists of a single fact table at the center, directly connected to multiple dimension tables, an arrangement that, as the name implies, resembles the shape of a star. Star schemas are designed primarily for monitoring data rather than deep analytical exploration, which enables rapid data processing. They are particularly well suited to high-scale information delivery, owing to the limited number of tables and the clarity of their direct relationships. The snowflake schema is an extension of the star schema. While the fundamental structure is similar, a fact table at the center surrounded by dimension tables, the snowflake schema introduces additional dimensions and subdimensions, which further normalize the data into more granular tables. This creates a more complex, multi-layered web of relationships that resembles the intricate branching of a snowflake. While this complexity increases the precision of data relationships, it also introduces greater query complexity. Understanding schemas is not merely an academic exercise, it is a practical necessity for any BI professional. Schemas directly influence how databases are constructed and how BI tools are built upon them. They are the output of design patterns and serve as the foundation for all downstream BI processes. As you progress in this course, you will have opportunities to engage more deeply with these schemas and even construct them yourselves. At this point in the lecture, please take the time to complete the reading activity for week 3. Read the handout provided and complete the associated quiz. This activity is designed to reinforce the concepts we have covered so far and prepare you for the material that follows. As we continue our discussion of data modeling and schemas, it is essential to appreciate that there are multiple facets of database design that a BI professional must consider. The framework of a database, encompassing how platforms are organized and how data is stored and processed, directly affects how that data is ultimately used. Consider, as a practical example, the database systems of a grocery store. Such a system must not only manage day-to-day transactions, but also support the analytical needs of decision makers seeking to understand purchasing trends and the effectiveness of promotions. Databases differ based on how data is processed, organized, and stored. It is therefore critically important for BI professionals to understand what type of database their organization uses, as this will govern the data models they design. A further key responsibility is facilitating database migrations, the process of moving data from one source platform to another. Migrations are often necessitated by technological change or organizational growth. They may involve adding tables or columns, splitting fields, removing elements, or changing data types. These are complex, multi-phase projects that require extensive testing and careful planning. Importantly, a migration is not simply a matter of replicating an existing schema in a new environment. It is an opportunity to redesign and improve. Databases can be classified along 3 primary dimensions: the manner in which data is processed, the way in which data is organized, and the physical storage arrangements employed. We will now examine each of these dimensions in turn. We begin with OLTP, or Online Transaction Processing Systems. These databases are optimized for processing transactions rather than for analytical work. They are designed to efficiently read, write, and update individual rows of data, ensuring consistency across business operations. A useful illustration is an online bookstore. When two customers simultaneously attempt to purchase the final copy of a book, the OLTP system ensures that only the customer who completes the checkout process first receives the item, and that the stock count is updated accordingly. OLTP systems are excellent for transactional integrity, but they are not inherently designed to read large numbers of rows concurrently. OLAP, or online analytical processing, systems complement OLTP systems by focusing on analysis rather than transaction management. OLAP systems can simultaneously draw data from multiple sources, enabling organizations to extract meaningful business insights. Returning to the online bookstore, an OLAP system might aggregate customer purchase data from multiple data warehouses to generate personalized homepage recommendations based on individual preferences. In many organizations, one of the first tasks for a newly appointed BI professional is to establish an OLAP system, providing the analytical capability that the existing OLTP infrastructure cannot offer. Database organization refers to whether data is stored by rows or by columns. In a row-based database, each row represents a single entry or instance, with all associated attributes stored together. This means that if you wish to calculate the average profit across 5 years of sales, the system would need to retrieve every row from that period, even if you only required a single column's worth of data. This can be inefficient for large-scale analytical queries. Columnar databases address this inefficiency by organizing data by column rather than by row. This architecture is widely used in data warehouses because it enables analytical queries to retrieve only the specific columns required, significantly improving processing speed. In our bookstore example, rather than pulling every row of data spanning multiple years, you could retrieve only the sales column, dramatically reducing the volume of data that must be processed. The diagram on this slide illustrates the architectural difference between row-based and columnar storage. In a row-based system, data is read horizontally across all attributes of each record. In a columnar system, data is read vertically. Only the relevant column is retrieved. The practical implication is that columnar databases are markedly more efficient for analytical workloads that require aggregation across large datasets. We now turn to the physical storage dimension. A single-homed database is one in which all data is stored in a single physical location. This approach is becoming increasingly uncommon, particularly for organizations managing large volumes of data. As cloud-based storage solutions continue to proliferate, the proportion of organizations relying on single-home databases will continue to decline. Distributed databases represent the more prevalent approach in contemporary organizations. In a distributed database, data is stored across multiple physical locations. A useful analogy is that of telephone directories. It would be wholly impractical to compile every telephone number in the world into a single volume. Instead, directories are partitioned by geographic region, distributed across multiple books. Distributed databases follow the same logical principle. Data is divided and distributed to make it more manageable and accessible. Beyond storage location, databases can also be distinguished by how storage and computational resources are arranged relative to one another. In a combined system, data is stored and analyzed in the same physical environment. This is a more traditional configuration that affords users access to all long-term data within a single system. However, as data volumes grow, these systems can become increasingly unwieldy and difficult to manage. Separated storage and compute systems address this scalability challenge by storing less relevant or archival data remotely while keeping frequently accessed, analytically relevant data locally. This separation allows storage and computational resources to be scaled independently, a significant operational advantage. For instance, an organization with large data volumes but relatively few active users conducting queries may not require proportionally large computing resources, resulting in meaningful cost savings. To summarize this section, BI professionals must maintain a clear understanding of several database framework characteristics. First is the system OLTP or OLAP in nature. This determines how data models and processes should be designed. Second is the data organized in a row-based or columnar format. This affects query performance and analytical strategy. Third, what is the physical storage arrangement? Single-homed or distributed, and combined or separated in terms of storage and compute? Each of these factors directly influences the design and effectiveness of BI solutions. We now arrive at the concept of the data warehouse. A data warehouse is a specialized type of database designed to consolidate data from multiple source systems, ensuring consistency, accuracy, and efficient access for analytical purposes. Data warehouses are the backbone of data-driven decision-making. They are typically managed by data warehousing specialists, though BI professionals play a significant role in their design. Having explored data modeling, schemas, and database types, we are now well positioned to consider how these concepts come together in the design of a data warehouse. When designing a data warehouse, BI professionals must consider several key factors. The first and most important is business need, understanding the questions the organization seeks to answer and the problems it aims to solve. Business needs determine how data will be used, stored, and organized. A hospital that monitors patient health outcomes has fundamentally different data requirements from a financial institution analyzing market trends to inform investment decisions. Defining business needs is therefore the indispensable starting point. Beyond business needs, BI professionals must also consider the shape and volume of the data. The shape of data refers to how information is arranged within tables, the rows and columns, and their configuration. Volume refers to the current quantity of data and its anticipated growth trajectory. Both factors have direct implications for how the data warehouse is designed and what model it will follow. The data warehouse model encompasses all of the tools and constraints of the system, including the database itself, the analytical tools to be incorporated, and the schemas that will govern data structure. Common schema choices include the star and snowflake schemas we examined earlier. The model is the overarching framework within which the data warehouse operates. To make these concepts concrete, let us work through a practical example. Suppose we are designing a data warehouse for a bookstore. Our first step is to engage with stakeholders to determine the business needs. In this scenario, stakeholders inform us that they wish to measure store profitability and website traffic in order to evaluate the effectiveness of their annual promotions. Armed with this information, we can identify the primary business process of interest, sales. With the primary business process identified, we can define the fact table. The sales table will serve as our fact table, containing metrics such as quantity ordered, total base amount, total tax amount, total discounts applied, and total net amount. These quantifiable measurements are the facts, the core data points around which the rest of the model is built. The fact table alone, however, provides limited analytical utility without contextual information. We therefore establish a series of dimension tables to provide that context. In this example, relevant dimensions include the store, the customer, the product, the promotion, the time period, and stock or currency information. These tables enrich the facts with the who, what, where, when, and how, enabling meaningful analysis. If we now examine the structure we have constructed, a single central fact table connected to multiple surrounding dimension tables, it becomes immediately apparent that we have created a star schema. This architecture is well suited to answering specific business questions such as the effectiveness of annual promotions. It also supports the creation of dashboards populated with key performance indicators and drill-down reports. The diagram on this slide illustrates the star schema we have constructed for the bookstore. The central sales fact table is connected to dimension tables for store, customer, product, promotion, time, and stock or currency. This visual representation makes the relational architecture clear. In practice, understanding this design logic enables BI professionals to build systems that are not only analytically powerful but also structurally coherent. It is worth pausing to consider why a snowflake schema may not be the most appropriate choice in this instance. Recall that the stakeholders' goals are to measure profitability, track website traffic, and evaluate promotional effectiveness, objectives that benefit from simple, fast query performance. Snowflake schemas, while more granular, involve multiple joins between normalized tables, which can slow down query execution. Star schemas perform markedly better for OLAP-style queries involving aggregations, summaries, and trend analyses. Snowflake schemas are more appropriate in very large, complex data warehouses where storage optimization is the primary concern. This concludes Lecture 3. In this session, we established the distinction between source systems, which ingest raw data, and destination systems, where data is stored and analyzed. We examined how data models and design patterns give rise to database schemas and explored dimensional modeling through its three core components: facts, which capture measurements; dimensions, which provide context; and attributes, which describe dimensions. These elements combine into fact tables and dimension tables, the building blocks of the dimensional model. We then examined the star schema, noting its suitability for high-speed data monitoring, and the snowflake schema, which extends the star architecture with additional subdimensions for greater granularity. We broadened our perspective to consider how database types, classified by processing mode, OLTP versus OLAP, data organization, row-based versus columnar, and storage arrangement, single-homed versus distributed, combined versus separated compute, directly shape the design decisions a BI professional must make. Finally, applying all of these concepts through the bookstore case study, we demonstrated how clearly defined business needs translate into a concrete data warehouse design. In this case, a star schema built around a central sales fact table linked to 6-dimension tables. In Lecture 4, we will build directly upon this foundation, examining data warehouse design methodologies and the pipeline processes that automate the movement and transformation of data.